Okay, welcome back to the second part of this first session. And our next speaker is Brian Anderson, who will tell us about two-dimensional quantum turbulence in Bose-Einstein condensates.
All right, thank you. It's a pleasure to be here, and I'd like to thank the organizers for the opportunity to come tell you about this work. What I will be discussing walks a bit of a line between Bose-Einstein condensation, which we're all familiar with, and some aspects of turbulence, particularly two-dimensional turbulence. And I know this is an area that many people in this community are not terribly familiar with. So what I'd like to do is start out with a bit of an introduction to turbulence real quickly, and then more specifically two-dimensional turbulence, and then make our way into talking about how we can study some two-dimensional turbulence physics in Bose-Einstein condensates. This talk incorporates some experimental results as well as theoretical results and numerical calculations. There's been a pretty big team working on this over the last few years, and the people listed in bold, Tyler Neely in particular, responsible for much of the data that you'll see. And on the theory and computational side, the group of Ashton Bradley at the University of Otago has primarily been responsible for the numerical results. Okay, so I'm going to start with kind of a picturesque way of looking at turbulence. And I'll admit right now that this approach is basically taken from one of my colleagues, Makoto Tsubota, who likes to use this particular video for introducing aspects of turbulence in classical fluids. So what we have is a picture of a dragonfly, and play this movie. And what you can see happening is something that we might sort of intuitively associate with the concept of turbulence. And I'd like to go a little bit more than this movie in talking about what turbulent flow might involve. There's many ways of defining turbulence. What I'd like to do is kind of qualitatively describe what is involved in typical turbulent flow. First, what we've got is the concept of energy being forced into some kind of long wavelength flow. And these regions circled in yellow show a bit of long wavelength flow. And turbulence typically will involve some kind of energy transport from these long wavelength flows into smaller wavelengths or larger wave numbers. And at the smallest length scales, energy is dissipated as heat. And this process is what is often desired to be described in turbulence. So what we've got in typical three-dimensional turbulence is the formation of large-scale flow structures that we can call classical eddies or vortices, decaying to ever smaller structures through some kind of disordered process that involves rapid mixing and transport of energy across many length and momentum scales. That's three-dimensional turbulence. The physical characteristics, what is very common is to look at a kinetic energy spectrum, how much energy is contained in different length scale flows or different wave numbers. And back in 1941, Kolmogorov showed that through dimensional analysis, through some basic assumptions, that the kinetic energy spectrum, E of k, is proportional to k to the minus 5/3. And on a log-log plot of this kinetic energy versus momentum, this would show up in measurements as this linear plot showing energy is proportional to k to the minus 5/3. This plot is the first measurement in a classical three-dimensional fluid of this kinetic energy spectrum, confirming this prediction of the spectral shape. But the physical mechanism of vortices decaying to ever smaller vortices, which we call the Richardson cascade, the linking between this physical mechanism and the kinetic energy spectrum, exactly how to go about doing that, that's still one of the open questions in the turbulence field. My talk is about two-dimensional turbulence, and that's quite a bit different in some fundamental ways to classical turbulence. And what I'd like to do is read a little bit of a story written back in the 40s entitled The Little Vortices Who Wanted to Play, and this will give a bit of an introduction to what's different about two-dimensional turbulence. Once upon a time, there were n vortices in a two-dimensional, frictionless, incompressible fluid enclosed by a boundary. Now, the vortices liked to distribute themselves in a completely random fashion, but they could not do that because they had too much energy. You see, they were not like molecules, which have more room and momentum space the more energy they have. Vortices had only a finite configuration space. So here's part of the key here. You can figure out that there is no way to take care of much energy unless you let at least one pair of vortices of the same sign get close together. The little vortices just pushed the biggest vortices together until the big vortices had all the energy the little ones did not want. And then the little vortices played ring around the rosy until you could not tell which was where, and it made no difference anyway. So the key idea here is some element of vortices of the same sign of circulation wanting to get close together. And this is counterintuitive. If you thought about vortex physics from Bose-Einstein condensation, the way we often describe vortices and condensates is by saying vortices of the opposite sign like to attract each other and then annihilate. Vortices of the same sign repel each other. It's actually quite a bit more complicated than that, and that's part of the subject of this talk. Okay, so this story was written by Lars Onsager, and that was a letter he sent to Pauling, but he did put this in a more accepted peer-reviewed type format. In 1949, his paper entitled Statistical Hydrodynamics was about trying to analyze how turbulence might occur in a two-dimensional fluid. He assumed that vorticity in the fluid was represented by point vortices, and he showed in this paper how vortices of like sign cluster together so that the unpaired vortices have more room to move. His approach was an equilibrium type approach trying to describe non-equilibrium physics. The applicability of his model to describing two-dimensional turbulence is still an open question, and we'll get back to that. But it is part of the feature of his approach to see or show how large compound vortices might remain as the only conspicuous features of the motion. And this comes about through, in two-dimensional convection, vorticity of every volume element of the liquid is conserved. Now, many of us know this paper, but for a different reason. It was in a footnote in this paper that he wrote that vortices in a superfluid are presumably quantized. So this is where we have taken our notion of quantization of circulation in superfluids. The reason this appeared as a footnote is because it wasn't the main subject of the paper. He wanted to talk about fluid dynamics and vortex dynamics, realizing that point vortex models for classical fluids might not be the most appropriate way to go or the most quantitative way to analyze vorticity. His footnote says, well, maybe this actually is pretty realistic if we look at physics in a superfluid. Okay, let's think for a moment about one of the quotes from this paper, large compound vortices remaining as the only conspicuous features of the motion, and think about where this might show up in physics. One conspicuous feature of the motion that's a large compound vortex can be seen as the great red spot on Jupiter's surface, and there have been numerous studies linking this to features of two-dimensional fluid flow and even two-dimensional turbulence. Jupiter is not a very good approximation to a two-dimensional fluid, but the surface, the atmosphere on Jupiter is very thin compared to its dimensions, and two-dimensional fluid dynamics does a pretty good job describing the flow. Okay. In the 1960s, Crichton took a completely different approach and did a full theoretical analysis of two-dimensional turbulence, and he showed that the Richardson cascade is reversed in 2 dimensions. Instead of the Richardson cascade being in three-dimensional turbulence where vortices break into ever smaller bits, in two-dimensional turbulence, vorticity grows through the process of merging. And in this process, energy will increase from small length scales up to large length scales, the opposite of what occurs in three-dimensional turbulence. And this process of this energy cascade process is an inverse cascade, inverse with respect to the direction of energy flux in three-dimensional turbulence, there is still the appearance of a k to the minus 5/3 energy spectrum, but in this case, energy flows from the small length scales to the large length scales. And this has been confirmed in numerous experiments. There's a picture here taken of tracer particles in electrolyte solution, and there's small scale stirring going on throughout the fluid, and with time, vortices start to merge together, and eventually this inverse energy cascade process turns off when very large scale flow has developed in the system. So this would be a large compound vortex remaining as a conspicuous feature of the motion. In this time period where you see this kind of vortex merging and swirling around process happening, there's experimental verification of the energy spectrum in the inverse cascade regime. And then in addition to this, and I won't go into this really at all, there's also a spectrum that is associated with what's called an entropy cascade. This is, we can think of this physically as vortex stretching, and k to the minus 3 portion of the spectrum shows up. So there are, one of the things to look for in two-dimensional turbulence experiments is the existence of this double cascade, a k to the minus 5/3, which we call the inverse energy cascade, and this k to the minus 3, which would typically be an entropy cascade. Okay, so how might we characterize the problem of turbulence? I like this quote from a recent book called A Voyage Through Turbulence. The role of vortex structures is seen as of central importance, while a statistical approach is needed to cope with the irregularity of turbulent flow at all scales. No fully satisfactory treatment combining these aspects has yet been found. In other words, what are the relationships between vortex distributions and dynamics and energy spectra? And this is at the heart of what we're trying to do in quantum mechanics. For two-dimensional turbulence, how well do Onsager's vortex dynamics and this statistical hydrodynamics approach, how well does that correspond with Kreitmann's energy spectra in his classical theory? So one problem in answering this question is that the point vortex model for describing classical fluid dynamics is a bit ambiguous. How do we describe classical flows with point vortices? How realistic is Onsager's model? And as I briefly mentioned, two-dimensional turbulence in a superfluid shows the appearance of quantized vortices, so Onsager's model becomes realistic. And this is where Onsager's footnote comes in. But this brings up another problem. There have been no two-dimensional quantum turbulence experiments yet in superfluid helium. This is extremely difficult to do. And this is where Bose-Einstein condensates come in. One possible approach to this problem is to use BECs to examine Onsager's model and try to link vortex dynamics with energy spectra. I'll go ahead and mention real quick. Throughout this talk, whenever I say two-dimensional, I do not mean two-dimensional or quasi-two-dimensional in the sense that we often associate it with BKT physics. The two-dimensional flows that I'm referring to in this project have to do with the limit in which flow in one direction, flow through one dimension, the velocity is uniform, there are no gradients, so we could have a fully three-dimensional system and still have two-dimensional turbulence or two-dimensional fluid dynamics if all the interesting flow physics happens in just one plane. Okay, so this is kind of the quick introduction to the way two-dimensional turbulence study might be relevant in a Bose-Einstein condensate. Let me introduce this a little bit more through an examination of what different regimes of turbulence might involve. There are many different aspects of turbulence. One is this dimensionality aspect, which we could put on one axis of some multi-dimensional problem space. There's also the aspect of the compressibility of the system, whether the system is incompressible with a constant density or compressible, like in a Bose-Einstein condensate. And then there's the aspect, I'll get that in a second, stopping right here. Most of the experiments that have been done in turbulence involve the three-dimensional limit through all various types of compressibility, incompressible fluid dynamics, compressible fluid dynamics. So that's one big bulk of the turbulence problem. There are a number of experiments in two-dimensional incompressible fluid dynamics, as well as compressible two-dimensional fluid dynamics. And what I'm interested in getting into is the quantum regime. So most experiments, turbulence, have been done in the classical limit, but there have been a number of experiments done in the quantum limit as well. Superfluid helium addresses turbulence in the quantum limit, but their experiments have been limited to the three-dimensional regime. With a superfluid helium, temperature can be raised or lowered above and below the critical temperature, and showing a correspondence between signatures of turbulence in both in the quantum limit that is the same as classical. Specifically, what I mean is this k to the minus 5/3 energy spectrum is seen both in superfluid helium as well as in liquid helium above the critical temperature. There have recently been some experiments of turbulence, three-dimensional turbulence in Bose-Einstein condensates in the group of van der Leyen-Beñato. And his experiments generate a bit of a tangle of vortices throughout the fluid. But the newest regime is this quantum limit of two-dimensional turbulence in a compressible superfluid. And this is the aspect of this huge problem space, or this big turbulence puzzle. This is where the experiments and theory that we're working on fits in. Okay. Oh, right. There are many other parameters of this problem. I didn't want to try to draw a cube that would fit all those, so I'll just mention that forcing and dissipation are big parts of this problem. We're still trying to understand much of this in a BEC, whether a system's rotating or not. There are other types of turbulence than the vortex turbulence that I'm referring to, wave turbulence specifically, but won't get too much of that. Okay, so to recap, a central problem of two-dimensional quantum turbulence is quantitatively linking Onsager's model, where the point vortex model is realistic, to Kreitmann's dual cascade theory for a realistic quantum fluid. And the main message of this talk, or what I hope to convey, is that BECs, or superfluid atomic gases, present some exciting new opportunities for studying and understanding two-dimensional quantum turbulence in an entirely new platform. What I'd like to see through experiments and numerics are answers to questions like, what kind of vortex distributions arise in two-dimensional quantum turbulence? What spectral signatures might exist? Can we see something like this k to the minus 5/3 spectrum? Can an inverse energy cascade be observed in a Bose-Einstein condensate? This has been an open question. Can large-scale flow develop from small-scale forcing? Is there this kind of end-time limit of a large conspicuous feature of the flow? Can vortex clusters develop in correspondence with what Onsager was talking about? And what are the roles of compressibility and temperature and trap shape and so on? Okay, so we've started some experiments along these lines to try to start to answer some of these questions. And the system that we've got in my lab in Arizona involves a highly oblate condensate. These are in situ pictures. This one on the left is looking down a tight axis and looking along the side in the plane of the trap. We see this pancake. What we see is a pancake-shaped condensate. In this trap, vortex bending and tilting are inhibited, and this puts us in the regime of two-dimensional vortex dynamics, but again, we're nowhere close to looking at BKT physics. The chemical potential is about 8 times the mode spacing in the tight direction. This is an experiment done with rubidium-87 with about 2 million atoms. Our temperatures are somewhere below 100 nanokelvin. That's about our critical temperature. And if you're interested, trap frequencies are 8 hertz by 90 hertz. We get lifetimes of about 50 seconds in these traps. Plenty long enough to do studies on vortex dynamics. I'll be showing you a bunch of pictures of condensates with vortices in them. If they're experimental pictures, like this one, they're all taken in expansion. We have to release the condensate from the trap in order to see the vortices and their distributions. Okay, so one of the first questions might be, can we even generate turbulence or two-dimensional turbulence in this trap? What might I mean by that? Highly disordered vortex distributions and a wide range of length scales throughout the distribution. We have found a number of ways to generate quantum turbulence in these systems. We can put a little bit of electricity in the trap and spin it, and we get a picture such as this one. And we can modify the trapping potential by turning on a blue-to-tune laser beam and either modulating the intensity of that beam or suddenly hitting the condensate with a laser, and that generates vortices, these disordered distributions. We can shake the trap. There are a number of ways to generate vortices and get these turbulent distributions, but there are a number of issues that come up in many of these methods. First of all, we don't really understand the excitation process, where the vortices come about, why they come about. We just know that they're quite easy to generate. There's pretty much anything you try in these highly oblate systems can generate vortices. We don't have ways of measuring the vortex dynamics. Because this is a the dynamics of the vortices are disordered, we can't just make a system, release it from the trap, look at the vortex positions, then do it again, and expect to see any correlation between one shot and the next realization of the experiment. One of the biggest problems is minimizing the additional excitations of the condensate, how much sound there is, or breathing oscillations of the condensate. So it is difficult to reach any kind of continuous injection of energy and vortices into the system, and we'd like to be able to do that in order to study some kind of continuously forced steady state turbulence. So there are a number of problems with most of the methods that we've looked at for generating quantum turbulence. One method that has worked pretty well is stirring the condensate with a laser beam. We take this highly oblate system, put a laser beam down the tight axis, and move this laser beam in a tiny circle. And the radius of the motion is captured by this little arrow here. And you can see that's much smaller than the radius of the laser beam. So really, the beam is just kind of doing this. And then it stops. After a third of a second, it has stopped. And what we look for is the vortex distributions that occur after that stirring has ended.
How many rotations is that?
Just one rotation. What we've found is that as a function of hold time after the end of the stir, that's on this top line, at the end of the stir, we have a vortex distribution that looks like this, or maybe one that looks like this, top and bottom row, identical conditions, but just different realizations of the experiment to show the variability from shot to shot under the same conditions. As we wait, that turbulent distribution decays, and in the decay process ends up forming in the trap what is a persistent current. In order to do these expansion measurements, we remove that central pinning potential prior to expansion, and the large vorticity that can exist around the pinning potential is shown by this, what looks like a large vortex in the middle. This decay process is not really the subject of my talk. What I'm focusing on is the turbulence process, trying to understand what's going on in the distributions and in the dynamics. So I don't want to focus on that so much, but just point it out as there is this feature of turbulence decay dynamics that is pretty interesting. Okay, so what do we learn from this process in the experiment? Small-scale forcing that leads to large-scale flow is possible. Small-scale forcing can generate vorticity. And in this process, what you can see in this image is that vortices are distributed throughout the system. In a movie that I'll show you in just a second, you'll see that the vortices distribute themselves pretty rapidly, and we have this corresponding experimental evidence. The vortex decay rates are slow. Vortices remain visible, so they stay aligned with a tight axis. We are in the regime of two-dimensional fluid dynamics. I'll leave it at that and get onto what we can't do. Unfortunately, in our experiments, we are not yet able to determine the circulation direction of individual vortices, measure spectra, or determine vortex dynamics. Some pretty important aspects of the problem that we don't have access to yet in the experiments. We do have access to friends that know how to run some complicated code. Actually, this movie is a fairly straightforward approach. It's a three-dimensional damped projected Gross-Pidievsky equation solver, and the initial conditions are the same, and the stirring conditions are as close as we can get to looking at what might be occurring in the experiment. So let me play this movie, and what you'll see is on the left a density distribution, and you'll see the stir occurring, and then this tiny stir generates vortices that rapidly distribute themselves through the system. We can sit and watch this throughout the whole process. Not going to worry about that initial stirring. The vortex distributions that are created and the dynamics that are created, I think, are what's interesting for this talk. So let me go on and focus on one little part of that movie. We can take a snapshot and look at vortex distributions and signs of vortex pairing or vortex clustering. Actually, in this movie, we only see signs of vortex pairing, so no cluster is bigger than 2. I've taken a time snapshot and look at the existence of what look to be pairs and circle them by these shapes. And I want to play this a portion of the movie again, and when I click go, I'd like you to look at what happens to these two vortices that are surrounded by this red circle. The shape will disappear, but just watch those vortices. So what we see is that these two vortices hang together for quite a long time. That's almost I think 2/3 of a second compared to the 1/3 of a second stirring. That's what we interpret as a potential signature of the kind of pairing or onset of pairing that Onsager might have been talking about. At the same time, there is a suppression of vortex annihilation, this is also part of Onsager's predictions. The pairing or clustering happens when vortices of opposite sign, their pairing up tends to not occur. So these two go hand in hand. From the simulations, we can also get kinetic energy spectra. The process of getting these spectra is a little bit tricky. This is a compressible fluid. We're interested in the incompressible part of the kinetic energy. I'll mention that again later, but I won't go through the process of extracting it other than to say we're looking at the part of the velocity field or the density-weighted velocity field that is divergence-free. Looking at the kinetic energy spectra as a function of time, by the end of the stir, we see this, what appears to be, on this log-log plot, this bilinear spectral shape. The forcing in our experiment occurs around this wave number, which is a length scale that's a few times bigger than the healing length. It's about the size scale of a vortex dipole if it's injected into fluid or formed by pushing this beam through the fluid. And what appears to happen is that there is this spectral form that is towards longer wave numbers. This line that I've plotted here has a slope of k is proportional to k to the minus 5/3. So it does look like we're forming some kind of Kolmogorov type energy spectrum at longer length scales than the forcing length scale. This is consistent with an inverse energy cascade, but does not prove that there is an inverse energy cascade. And then for these shorter length scales, we have a k to the minus 3 structure. In our case, this is nothing to do with an entropy cascade. It is only to do with the shape of the vortex cores, and I'll get to that in just a second. Okay, so it looks like we've got some kind of tantalizing evidence from those simulations that there is possibly some correspondence with inverse energy cascade and what can occur in a Bose-Einstein condensate. We can approach this problem analytically from the perspective of the Gross-Pedievsky equation, and this is quite an involved process to explain, so I won't explain it. I'll just highlight a few of the most important elements of it. I mentioned that there's a decomposition process for looking at the incompressible portion of kinetic energy. That's what this slide is about, and I don't have time to go through that. But that is what we're focusing on in this approach. There is a numerical solution we can get for the shape of a vortex core. So this is plotting the density versus position away from the center of a vortex core, comparing a numerical solution with an ansatz that is given here. And the nice thing about this ansatz is that we are able to take Fourier transforms and look at momentum distributions or distributions over wave number. What we find is that for a single vortex, there is this k to the minus 3 slope that occurs in the energy spectrum. That is where this k to the minus 3 being only to do with the core structure comes in. Okay, there's too much to go through here, so I'm going to skip this other than to say that we can get a total kinetic energy spectrum for a set of vortices, and what we find is that there are particular distributions that do show a k to the minus 3 spectrum in part of the range of wave numbers, and the k to the minus 3 part still sticks around. So this is a statics approach, no dynamics here, just saying that we can find ways of getting k to the minus 5/3 in the spectrum. So this brings up a proposition for how an inverse energy cascade can form. We suppose that there may be injection at one wave number, and then vortices cluster together and develop a k to the minus 5/3 part of the spectrum. We wanted to see this in numerics, so we did a simulation with superfluid flow past 4 static barriers and looked at the formation of the vortex field downstream, and in analogy with two-dimensional thin film experiments. And in our case, we saw that there is, in the dynamic sense, what looked to be close to a k to the minus 5/3 spectrum developing downstream. And I'll note that the green and red lines showing these two different spectral slopes of minus 3 and minus 5/3, those are not fits. They're not there to guide the eye. They're there from the analytical approach. And this is one of the really exciting things about studying two-dimensional quantum turbulence, I think, is that we've got this potential analytical approach to describing these spectra in a completely new way. Plots here, which I won't go into, show evidence of clustering. And one of the significant features of this is that it says if we can measure the vortex distributions in a condensate, we have something that we might be able to substitute for measurements of kinetic energy spectra, which are pretty difficult. Okay, so this is essentially my last slide. Our experimental challenges are still figuring out how to sustain a turbulent state with minimal heating and atom loss, figuring out how to develop statistical measures, how to measure momentum and energy spectra. We are working on ways of looking at vortices in situ. We've had some success looking at vortices directly in the condensate without having to expand. What we want to do now is push that technique into looking at vortex dynamics in real time. And my conclusion of the talk is that there's still plenty to do, but I do think we're on our way to developing an understanding of this particular corner of this big turbulence puzzle, and hopefully, maybe, help understand some more general aspects of turbulence. So I'd like to end by thanking everyone who's been involved with this work on this list. It's still ongoing, involves many different parts of it. And thank you for your attention.
Yeah, thank you very much. Any questions? Nothing.
What could be a tangential problem that there is an article that Univ long time ago, in '98, that showed that in the two-dimensional condensate where the water under water square approaches to the sound, the whole thing gets mappable to one of the partial differential operations, which is called current redistribution, and everything becomes more stable. Do you think this that it brings something new to
Yeah, so this is an aspect of the compressibility of the system. The fact that the system is compressible, there is this, I don't know if the resonance is the right word, but there's this particular wave number or length scale at which vortex anti-vortex pairs will annihilate and turn into sound, or the reverse process happens. And that length scale is where this kink is in the spectrum. And I think one of the most important things in this line of work is to understand how that process happens. What is going on in the physics of this vortex anti-vortex annihilation? And that's one of the things I would love to be able to study in the experiment. And we're trying to figure out ways to do that. I think it's a super important aspect of it.
We've been trying to think of physical picture of seeing, in 2D, your structures just get bigger, and in 3D, they sort of break up.
Yeah.
Is there sort of, is there some dimensionality argument that I can see that this has to happen because in 2D I don't have space somehow?
So in 3D, what you can have is, if you've got a 3D box and a vortex going through the length of the box, that vortex can bend around. And so there is no conservation law for the net vorticity about, say, this direction. So the vortex stretching that can occur, or the bending, or the interaction of different vortices that are three-dimensional in shape, vortex rings and lines, that doesn't exist in 2D. So it's that extra conservation of vortices can't bend, they can't cross and form rings, that conserves that the vorticity and keeps stretching from occurring in that third dimension. So even in a three-dimensional fluid, if you can somehow turn that off, meaning no significant gradients of velocity, at least in that third dimension, then you can get two-dimensional dynamics.
So, I have a naive conceptual question, which you probably hinted at, but I'm not sure I got it. It's a bit related to my efforts to distinguish transient and intrinsic non-equilibrium effect. So you were talking about the ways you can induce these vortices, and there are many, but they're very similar to what other people in the field use to study equilibrium distribution, like because of lattices, right?
Yeah.
And indeed, in your case, also, eventually it reached some equilibrium distribution, which in your case was spinning of all the vortices to the zero density region in the center where the laser was, right? And so I was just wondering whether there's a sort of conceptual qualitative question there about what defines turbulence or chaotic behavior. Is it the same thing if you just look at short times, or if there's an intrinsic property of the system that the system fundamentally cannot reach equilibrium, right? Do you have to study a system which cannot reach equilibrium in order to study turbulent dynamics, or is it okay to look at short times? Is there a conceptual distinction there?
I think there's a whole lot wrapped up in your question. So there are aspects, you touched on the idea of chaos versus turbulence. And you can study chaotic dynamics in potentially 3 or 4 vortices. And I'm not really talking about that. There are links between chaos and turbulence that I'm not addressing here. As far as approaches to equilibrium, dissipation, our finite temperature, non-zero temperature, for those of you who are at NS, is an important aspect of this as well. And so the process of vortex decay does come into this. There is vortex anti-vortex annihilation that does occur in the decay process. Vortices are lost at the boundary. There are two pretty distinct directions for study of turbulence. Forced cases where turbulence is forced, and cases where there's turbulence in the system, the forcing is turned off, and you look at what happens during the decay process. I'd like to be in the forced turbulence regime. And if we can get in the forced turbulence regime, we're always out of equilibrium.
Yeah, no, I understand.
And the process of reaching equilibrium is a completely, I think, fascinating topic. And how that actually occurs is, I don't really know.
Yeah. No, I understand that that's the safe regime where you would like to be. But I'm saying when you're not, is there some general belief that at short times you're still looking at the same physics? Or
Same physics as what?
as when you were in a forced, if you're in a forced turbulent regime, or at short times in the decay regime, is it supposed to be the same physics? Is that
I think there's enough different physics that you can have many of the same aspects, and it's dependent upon the system and the dissipation parameters that, well, so in say soap film experiments, you can study either this forced regime where you're always seeing an inverse energy cascade, or you can study this regime where you're only seeing an entropy cascade without an inverse energy cascade developing. And I think that would be, if I understand it right, which I don't understand all the classical turbulence aspects, but I believe that's a decaying turbulence regime. You can see that in forced turbulence as well. There are soap film experiments where you can see both the inverse energy cascade and the entropy cascade regime. So it's probably not being clear on this, and it's not clear in my own head, but aspects of both, physical aspects that appear both in forced and decaying turbulence, as well as aspects of just forced or just decaying turbulence.